So in this video, we're going to talk about covalent bonds, okay? So a covalent bond is a bond that's formed by sharing electrons between two atoms. And so what do I mean by that? All right, so here we have two nuclei, right? So two different atoms, okay? Their nucleus, or their nuclei. And so covalent bonds is basically when you have two different nuclei and they're sharing a pair of electrons between the two, okay? And this is what bonds these two atoms or the two nuclei together, all right? And so unlike ionic compounds where, when we talked about ionic compounds, like for example, if we're talking about Na and Cl, right? We know that sodium has 1 valence electrons, chlorine has 7 valence electrons, okay? And so due to a huge electronegativity differences, the electron of sodium is taken away and given to chlorine, all right? And so now what happens is that sodium has a positive charge, and then you have chlorine that has a negative charge. And so due to this, there is an attraction between the two because of the opposite charges. There are electrostatic attractions. That's essentially what it is. All right. And that's ionic compounds. But when covalent compounds, basically, you have two different nuclei, two different elements, and basically all they are attached to each other by the sharing of a set of electrons. Okay, and so that's kind of one of the biggest difference between the two. Now, when we have these type of compounds, we call these compounds molecules. Okay, and I know sometimes we use molecules interchangeably in like everyday language, but a molecule is a compound that the atoms are held together by covalent compounds. While ionic compounds, we call these guys formula units. Can't spell formula. Let's try that again. All right. Formula units. There you go. Much better. All right. So that's the biggest difference between the two. So much like ionic compounds, in where each of the elements or each of the atoms are doing their best to attain a noble gas electric configuration, right? And if you notice, like if you look at here, just to give you a quick example, we look at this chlorine. It has 8 valence electrons. Sodium in this case also has, a full set of valence electrons. It just lost that first set. So let me just go ahead and illustrate this so you can see what I'm talking about. If you draw the Bohr's model of sodium, we see that its first row has 2 electrons. Its second energy level has 8 electrons. And then the neutral atom has a third energy level that only contains 1. Well, when sodium, in this case, loses the electron to the chlorine, so chlorine could become a chloride ion. So essentially what happens is that this whole outer energy level disappears, right? There's no electron. It doesn't disappear, but there's just no electron, which then leaves it that now it has a full valence shell, much like a noble gas. All right, and so ionic compounds basically work by these guidelines, right? By this dogma, if you want to say, where they're looking to gain this electron configuration of a noble gas. Now, covalent compounds, it's pretty much the same way, all right? But this time it's just through the sharing of electrons. And so what do I mean by that? Let's consider hydrogen, right? So I don't know why I keep on using a highlighter. Let's consider hydrogen. So we have 2 hydrogen atoms. Each of them have 1 valence electron, okay? And so they can't rip electrons away from each other. They're the same atoms. They have the same electronegativity, so that's not going to happen. But what they're going to do is that they're going to actually share these electrons between themselves, all right? And when you look at it, If you think about how many electrons this hydrogen to the left has access to, you will say it has access to electrons, much like the noble gas helium, right? And then if you consider this hydrogen to the right, well, it also has access to two electrons, much like helium. All right. And so in this case, through the sharing of electrons, now these nonmetals that are bonded together both have an electric configuration of a noble gas. So let's look at another example. All right. And I want to let's consider chlorine. So let's say we have two chlorine atoms that are going to bond to one another, right? And we know that chlorine has 7 valence electrons. Okay. Now they're going to bond to one another. All right. And so what's going to happen is that they're going to share a set of electrons. All right. So that way, when we kind of draw the diagram here, okay, they're going to share these 2 electrons here. All right. And by doing that, okay, if you look at the left chlorine, by doing this, now this chlorine has access to 8 valence electrons, much like the noble gas argon, which is next to it, right? And then this chlorine also has access to 8 electrons, 8 valence electrons, all right? And so if you see here, they're sharing this set of electrons here in the center, all right? And by sharing these electrons, now each atom has access to 8 or full set of a valence shell, much like a noble gas. Now, in a covalent compound, we have to consider what we call bond length, right? Now, what is bond length, right? Bond length is the optimal distance between 2 nuclei. So we have our 2. So I guess if we were to consider, I guess, the letters here to be our nuclei, right? The distance between the 2, all right, will be our bond length. Now, what affects or what factors causes the length of a bond? Well, you have to consider this, all right? So in here, right, when we're looking at these atoms and this molecule here, okay, what's going to happen is that you're going to have a repulsion effect. And actually, let me just kind of clean this up a little bit so that way it kind of makes sense. So I'm going to get rid of these circles. Okay. So you're going to have this repulsion effect between the 2 nuclei, right? Because they're both positively charged. And so because they're positively charged, they're going to repel each other, okay? Naturally. All right. And also you're going to have the repulsion effect between these electrons, all right? Because these electrons are close to each other, they themselves are going to repel, okay? Now, but at the same time, you're going to have this huge attractive forces, all right, between the electrons here and the protons in the center, all right, and the protons and the nuclei, okay? And when these repulsion, so when the repulsion force is equal to the attractive force, so when you have the repulsion forces of your protons and proton, all right, the nuclei, and the electrons of one to electrons in the other atoms, and it's equal to the attractive force between the proton and the electrons of each of the atoms. When they're equal to one another, all right, this equal force will then determine the distance between one nuclei and to the next, all right? And when the repulsion and attractive force are equal to one another, then that's when the distance is established, okay? And so what does that mean, all right? Well, for atoms who are typically smaller, so let's just say hydrogen, right? Or not atoms, molecules, where the atoms that makes up the molecules are smaller, all right? the attractive and repulsive forces are not as strong. So the nuclides could be much closer to one another. Versus if you were to have like iodine, for example. All right, iodine is a much larger atom. All right, where you have quite a few energy levels, right? And so I'm just kind of sketch this out. So they have quite a few energy levels. And so because there's quite a few energy levels, the distance between the two nuclei is going to be much further apart because there's a much stronger repulsive force. And at the same time, there's a stronger attractive force as well. And so because there's a much stronger repulsive force, the distance between those two nuclei is going to be much larger versus the distance between the two hydrogens. All right. And so it's one of those things that we must consider. Now, and you'll notice when I was giving examples of covalent compounds, I was using elements that were using atoms, two of the same atoms to illustrate this. But in nature, there are 7 elements, or 7, I would say 7 elements, where in real life they are never by themselves. Okay, and so we call them the diatomic molecules. Okay, because most cases, well, can't spell today, I apologize, diatomic molecules. All right, because in nature, when we say these elements, they always come in pairs. All right, and you kind of need to know these pairs. And as we're going, when we later on talk about chemical reactions and stuff like that, every time we say these elements, these atoms, these molecules always come in pairs of 2s. And so let's address them. All right, so they are, you have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and finally fluorine. All right, and so these guys always come in pairs of 2s. All right, and so when we say, hey, yes, this is bromine, think Br2. When we say oxygen, we breathe in oxygen, it's O2. Chlorine gas is a yellowish poisonous gas, Cl2. There's nitrogen. About 70% of our atmosphere is nitrogen, N2. Okay, and so you need to know these 7. The way I memorized the 7, and actually when I was writing it down, I was kind of saying in my head, this word here, it's like a funny last name, Brinkelhoff. I think of Brinkelhoff. It's a funny name, and I think just because it sounds kind of humorous, it sticks in our head a little better. So Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. All right, so these are the 7 diatomic molecules, and we need to just make sure we know those. Okay.